Hi, everyone, and welcome to our discussion on wave interference. We're going to talk today about the principle of superposition and really what that looks like, what the application is for that. And then we're also going to talk a little bit about standing waves and fundamental frequencies. Now, standing waves and fundamental frequencies are not going to be showing up on your AP Physics 1 test, but we are still going to go into a little bit of wave discussion so that you're prepared for that next step for you. So the principle of superposition states that the result of a wave overlap is going to be your algebraic sum of the different displacements. So what that means is we can have constructive interference or destructive interference. Constructive interference is when the wave pulses are going the same exact direction, they end up adding to each other. Destructive interference is when wave pulses are going opposite directions, they destroy each other or they subtract from each other. So the way I kind of look at it is if you have a pulse above the x-axis, then that's a positive pulse. If you have a pulse below the x-axis, that's a negative pulse. And then you're adding those values together. So a positive, you add the stuff on the top and you subtract the stuff on the bottom. And it all depends on how they overlap with each other. So we're going to look at some examples. When we look at this first example right here, we're looking at a wave pulse that's being sent down our string, we'll say. So when we look at this wave pulse right here, we're looking at a wave pulse that's going to be sent down this string. And so what that is the wave pulse, it's almost like it's going this direction over time. And each section in your x-axis is a unit of time, 1 unit of time. So what we want to first see, it says a wave pulse is shown traveling to the right along the string at a speed of 1 unit per second. The shape of the string is shown at time t equals 0. So this is almost like I've taken a very quick still image of something that's moving. So it's just a snapshot of what that pulse looks like in a moment, but it's very much a moving object. So in the next moment, it's going to have moved down that string. So the first question is this a mechanical pulse or is it non-mechanical? This is definitely a mechanical pulse. And is it transverse or longitudinal? Well, you have your disturbance up and down and your energy transferring that way. So that's going to be a transverse pulse. Okay. The next question is, as the pulse passes through point P, that point on the string moves. What direction is point P moving at each time? So if I'm moving along, this is what it looks like at 1 second. Okay, and then I'm going to go 2, 3. This is going to be 3 seconds. So at 1 second, it's going to be at your 0. So it's going to be standing still. It's not going to be moving. But point P, this part is going to be at point P. So right here, it's moving up. The pulse is moving up. So that's going to be moving up. And then at 4.5 seconds. So I have 4 and 4.5 is right here. So at 4.5 seconds, again, it's standing still. It's not moving. Okay. And then the next one is at 5.5 seconds. At 5.5 seconds, it's right here. And it's going back down to equilibrium. So it's going to go down. At 6.5 seconds, it's standing still. And at 7.5 seconds, we're looking here, it's moving back upwards. So it's going to go up. Okay. It says, what is the average speed of point P during the entire time interval required for the entirety of the wave pulse? So if we look at it, we're going to look at what is the distance divided by the time. The average speed is going to be our distance divided by our time. Well, the time in which we're looking at this pulse, the time that it takes to travel is going to be 6 seconds. So what is the distance going to be? Here I have the distance here, and then I'm going up from 0 to 3. So I'm going up 3, and then I'm almost staying still, no distance. And then I'm going down from 3 to -2. So I'm going down 5. So I have 3 plus 5, and then standing still here, and then going up a total of 2. So plus 2. So that's 3 plus 5 plus 2 is 10. So I have 10 divided by 6. That's a speed of 1.67 meters per second. And then the last question that's not on this screen but is on your sheet of paper, it says, during which time listed above is point P moving the fastest? Well, where it's moving the fastest is where it's going to have the fastest slope. So it's going to be moving the fastest right here, okay, where I've boxed. And then it says calculate the fastest speed. So we're looking at the speed. Well, the speed at the fastest point is going to be a change in distance is going to be 5. And the time that that takes is going to be 1 second. So this is going to end up being 5 centimeters per second. And then down here where I have 1.67 for this speed, this should be centimeters per second. Okay. So moving on to question number 9, it says a wave pulse is shown traveling to the right along a string at a speed of 1 unit per second. The shape of the string is shown at time t equals 0. Between times 0 and 5 seconds, the entire pulse moves through and beyond point P. On the coordinate axis below, plot the velocity of the piece of string. So the velocity, remember, this is a position versus time graph. And to refresh your memory, the slope of a position versus time graph is going to be your velocity. So your slope, when I'm looking at that, at first, for my first 2 seconds, this is going to be my first right here. I have there and there. So that's going to be for my first 1 second. I have a change in 2 divided by 1. So I have a velocity of 2. For my next second, I'm standing still. So I have not changed my distance there. For my next 2 seconds, I'm going down, and I'm going down 2 divided by 2. So that's going to end up giving me -1, and that's going to last for 2 seconds. And then from 4 to 5, I'm back to 0. And so hopefully this right here was a review of our distance versus time graphs and our velocity versus time graphs and how those are related. So again, position versus time, the slope of a position versus time graph will give you your velocity. Now, moving on to some more information about waves, we're going to look at a wave created on a string such that it completes 1.5 cycles every second. So cycles per second, that's going to end up giving me my frequency. The wave moves 12 meters along. That's going to be my change in x along the string's length in a time of 0.8 seconds. So that's going to end up being my time. Calculate the wave's speed. So when I'm looking at speed, I'm looking at the distance divided by the time. My distance in this case is 12 meters. My time is going to be 0.8 seconds. And so that's going to end up giving me a speed of 15 meters per second. Now, the next question says, figure out the wavelength. Well, I know that velocity equals frequency times wavelength. And I know my velocity here is 15 meters per second, and I know my frequency is 1.5 cycles every second. So I know that my wavelength is equal to my velocity divided by my frequency. My velocity is 15 divided by 1.8. I can include my units here, meters per second and 1/seconds. I show that seconds cancels, and I end up getting my wavelength is 10 meters. Okay. Moving on to question number 11. Question number 11 says that in each of the following diagrams, 2 wave pulses are shown traveling towards each other on a string, moving at the same speed. For each diagram, draw the shape of the string a moment when the centers of the 2 pulses exactly overlap. So for this first one, after 1 second, okay, it's right here. After 1 second, it's going to end right here. This one, after 1 second, it's going to end right there. Then this one right here, this wave right here, after another second, it's going to end right here. And after 1 second, this one's going to end here. So I have a pulse going up by 1 and a pulse going up by 2. So when I add those together, I'm going to end up, they're going to add together. They're going to displace completely. And it's going to be a displacement total of 3 squares up. Okay. So then this next one is a little bit more challenging. Okay. After 1 second, we're here. And after another second, my end of this one is like this. So I'm going to draw this one right here. Okay. Then for this one right here, after 1 second, it's here. And after another second, it's here. So now I have this up and that down are going to cancel. So what I end up having is the displacement of 1 unit up and 1 unit across. So I'm going to have something that looks like this, just in that section. Okay. And again, this is the law of superposition. Basically, it's saying that when I have wave pulses cross each other, I'm going to have some kind of interference pattern. And this is going to be important as you move on in physics and you study sound. So this question actually comes from a previous AP Physics 1 test. And when I look at this question, I'm given that a wave pulse is going towards a wall. And what I'm being asked is the wave is moving towards the fixed end of the string. Draw the wave pulse 8 seconds after the moment pictured. So 8 seconds. So this pulse right here has gone 1, 2, 3, 4, 5. It hits the wall at 5 and then reflects backward 6, 7, 8. So then it's going to reflect, because it's fixed, it's going to reflect down and it's going to follow the same exact pattern. So here I went up 2. So I'm going to go down 2, up 2, and then I have this little part that was down is now going to go up. So it's going to be reflected, but have the same amplitude and the same velocity. Everything else is going to stay constant. So this is going to be my reflected pulse at that point. So at 8 seconds, that's what that's going to look like. We are not going to do practice problem number 13, so go ahead and move on from there. And now we're going to look at standing waves. So when I look at standing waves, you can see the waves moving, but what ends up happening is when these wave pulses cross each other, you end up getting this standing wave pattern. And so if you look right here on the left-hand side, if you look at it through a strobe light, you kind of get these antinodes and nodes. The nodes are these parts, the pinched parts. That's a node. Okay, here's another node. My nodes, like I said, are the pinched parts. And this right here and that right there, that's called my antinode. Okay. When I have, basically I have wave pulses that go down and then they come back, and the reflection and the incident pulse and the reflected pulse end up crossing each other and interfering with each other. Okay, so standing waves happen on a string or a spring when waves move in both directions with the right frequency to keep producing interference effects at the same time, your constructive and destructive interference. So it almost looks like that wave is standing still. Again, if you look at it through a like a strobe light. So standing waves can also be excited in columns of air, such as soda bottles. Have you ever blown through a soda bottle and then you can make different sounds, and then you add a little bit of water and it makes a different tone? It has a different tone. You add a little bit more water, it has a different tone. You have a different frequency that you're hearing, okay? So that, or another example would be like if you put water in like a glass and you run your finger along the edge of the glass and it makes that sound. That's another example there. Okay, so what do we do? What are we going to do here? Well, we're only going to look at, for this class, we're only going to look at standing waves that are fixed end. So standing waves that are fixed end, we have our first harmonic, second harmonic, and so on and so forth. So our first harmonic, our lowest frequency, our first fundamental frequency, it's our lowest frequency, can be when I send a wave pulse in and it's reflected back, okay? So if you look at that, the length here is equivalent to 1/2 of a wavelength, right? And so the length is equal to 1/2 of a wavelength. So if you look at it, we know that frequency is equal to V over wavelength, right? And here, because we know this, we know that that's equal to V over 2L. Well, then the next one, we have a full wave, and then it's reflected back. Okay, that's second harmonic. So in this case, our length is a wavelength. So then for our second frequency, this was our first fundamental frequency. For our second frequency, you end up just having V over L. And then right here, you can do it again, okay? And so on and so forth. And you start to realize that you have this pattern. So to figure out the frequency of your standing wave depends on which harmonic it is. And you're going to use this equation. Frequency is equal to N times V over 2L. We're not going to use this tension on a string equation, but you have seen that twice in this presentation at this point. Okay, so again, your fixed and standing waves look like this. Your first fundamental frequency or first harmonic, your first overtone, which is called your second harmonic. Your second overtone is called your third harmonic. So here I have waves. Waves are able to travel on a certain 20 centimeter long string at a speed of 90 meters per second. This string is connected to an adjustable oscillator, and as the oscillator's frequency is adjusted higher and higher, standing waves appear on the string at certain frequencies. As the frequency is adjusted up from 0, what is the fourth frequency? So we're looking at frequency 4. We want to know what frequency 4 is. Well, let's see. The waves are able to travel on a 20 centimeter long string at a speed of 90 meters per second. Okay, so let's look at our first fundamental frequency, or our first harmonic. So we have V over 2L. Well, our V is 90 meters per second. And then our 2 times L, which is 0.2 meters, is going to end up giving us a first frequency of 225 hertz. So that's our fundamental frequency. So our fourth frequency is going to be 4 times that, is going to be our fourth frequency. And that's going to be 4 times 225 hertz. Which ends up giving us that our fourth harmonic is equal to 900 hertz. And we only have 2 more questions that we're going to look at, and that's going to be the deepest that we're going to go in this class with standing waves, okay? There's so much more than you can cover, though, and if you're interested in it, or if you're really into music, it's really worth you researching and looking into. Okay, so the string in the picture is 45 centimeters long and is vibrating at 330 hertz. What is the fundamental frequency? Well, the first thing that's important to me is that you know which frequency is being shown. Well, we have our first, our second, and our third. So this right here is our third frequency. So our F3 is 330 hertz. So we have F3 is equal to 3F1, okay, which is equal to 330 hertz. So that tells me that my fundamental frequency is 110 hertz. Then it says, at what speed do waves travel on this string? Okay, well, if we look at this question, we know F is equal to V over 2L, okay? And so we know V is equal to F times 2 times L, which is going to be equal to 110 hertz times 2 times my 45 centimeters or 0.45 meters. That's going to end up giving me a speed of 99 meters per second. And then our last in-class practice problem that we are going to go over for this class, yay, congratulations, is in-class practice problem number 16. Two successive harmonics of a vibrating 40 centimeter long string are 225 and 300 hertz. What's the fundamental frequency? Well, here's the deal. If I do Fn minus Fn minus 1, okay, I'm going to end up getting my fundamental frequency. So if I look at it, I just need to take the difference between here. So 300 hertz minus 225 hertz, and that gives me 75 hertz is my fundamental frequency. Which harmonic is 225? Well, I know that NF1 is equal to 225. So N is equal to 75 divided by 225. How many times does 75 go into 225? N is equal to 3. So it's the third harmonic. And then finally, it says, what is the wavelength of the waves on the string when oscillating at its fourth harmonic? Well, if we draw that, we have our first, second, third, fourth, okay? And then it's going to come back around. That's what our standing wave is going to look like, okay? And the length of that is going to be 40 centimeters. Okay, so I know lambda 4, okay, is equal to 1/2 times 40. And this is because I have two wavelengths here. So I have 1/2 40 centimeters. So my wavelength is going to be 20 centimeters. Okay, looking at this, when I'm looking at this, I know two wavelengths is equal to 40 centimeters when I'm looking at the fourth wavelength. Okay, and so that's where I end up going from here to here. Okay, just if you needed clarification. Hopefully that was helpful, and hopefully you have enjoyed these videos, or they have at least helped you out a bit.